Welcome everyone. Before we begin, I'd like to thank my supervisors, Professor Reitano and Dr. Lombardo, as well as all the members of the committee and all of you for being here today. The topic of my presentation will be new developments in silicon and multi-junction photovoltaics. So here's a brief overview of today's presentation. I'll begin with a brief introduction of silicon photovoltaics and of the key figure of merit that will guide us through the presentation. Then I'll move to the definition of the bifacial photovoltaics, its advantages and its characteristics, along with a study on the field and a MATLAB model that I employed to run some simulations. Next, we have the multi-junction photovoltaics. I'll explain its new features and its advantages. And also in this case, I have employed a Python a Monte Carlo algorithm to run some simulations in order to optimize a case study of the two junction systems. In the final part of the presentation, we will mix together these two approaches, the bifacial one and the multi-junction one, and I'll present a case study of a prototype that we realized and tested in the field in order to increase the efficiency of the system. I'd like to start with these cool pictures, the picture that shows the potential energy production of various energy sources, renewables and non-renewables, compared to an estimate of the Earth energy consumption. As we can see, in the case that interests us, solar is more than enough to provide enough energy for the whole planet. But without delving too much into the details of these estimates, the main point here is that this study assumes that more or less the totality of the continental land is occupied by solar panels. This is, of course, not feasible, both economically, industrially, maybe even physically. So, the main point here is that the more efficient a system is, the less space, the less modules, the less materials will be required to achieve a significant amount of renewable energy production. So the main point of the presentation is to increase the system of photovoltaic systems. Let's start from the basics, and a solar cell is essentially a p-n junction that is formed when an n-doped semiconductor is put in contact with a p-doped semiconductor. In this case, we have a diffusion of electrons from the n region to the p region and a diffusion of holes in the opposite verse, creating what is usually called a space charge region or depletion region, where we have an electric field that balances the diffusion between holes and electrons. So here we have the Venn diagram of the system, and whenever a photon of suitable energy, where suitable means higher than the band gap of the semiconductor, is absorbed, we have the formation of an electron-hole pair, and these carriers are accelerated by the electric field towards the metal contact. And this is the current that we are able to collect and to extract energy from. Usually, the solar cell is synthesized as with a lumped element circuit model, where we have a current source, a diode, which represents recombination effects in the cell, a shunt resistance, which represents alternative paths for the current inside the cell. So this is all current that is not collected by the outside system. And lastly, a series resistance, which represents usually the contacts along the cell or along the string in a solar module. Here is the characteristic current voltage equation. And here we have a general plot of how this function appears. We have some key parameters that are employed when analyzing the performance photovoltaic system, namely the short circuit current for a voltage of 0 volt, open circuit voltage for a current of 0 ampere, and if we plot in red the power produced by the system, the power at the maximum power point. Here I have also added a dashed line, and this represents the same equation, including the effect of the shunt and series resistance. In fact, usually the series resistance can be estimated by the slope, the inverse of the slope in this region, while the value of the shunt resistance can be estimated by the inverse of the slope in this region. The key parameter, as we said, is the efficiency, usually called the power conversion efficiency, and is defined as the electrical power delivered by the system over the incident optical power, which is given by the irradiance times the area of the photovoltaic system. The most important work in this field is the one published by Shockley and Kaiser in 1961. In this work, it has been used the detail balance principle. That is, they have identified incoming energy towards the system and a balance between generation and recombination process, between each phenomenon and its opposite, in order to obtain the ideal current voltage characteristics of a solar cell. In doing so, however, they excluded all non-radiative recombination process in order to, let's say, approximate the highest or the most ideal system possible. So here we see a diagram of the most important recombination processes. We have the Shockley-Rideau recombination, which is assisted by trap level inside the forbidden gap. The radiative recombination process, which is basically the opposite of the photon absorption. And this is the one that Shockley and Kaiser considered for their work. And lastly, the Auger recombination, in which the energy derived from the recombination of a whole electron pair is absorbed by another excited carrier and is then lost via thermalization in the semiconductor lattice, basically. With this hypothesis, Shockley and Kaiser derived an efficiency, the highest possible efficiency for a silicon solar cell that is close to 34%. During the year, this estimate has been refined by including other fundamental processes that cannot be eliminated, such as the Auger processes that have been seen previously, the optical properties of the materials, because Kaiser and Shockley also assumed that every suitable photon was absorbed. Other phenomena such as free carrier absorption, where a photon is absorbed by an excited carrier and the energy is again lost via thermalization. And with all these refinements, the final estimate, which is accepted by most of the scientific community today, is 29.4% for silicon. And here we see a chart published by NREL, which shows the record efficiencies over time. I have stressed the results belonging to silicon solar cells. And this red line I have added corresponds exactly to the value of 29.4%. This is to give an idea how close we are to the efficiency limit. At the moment, the highest record should be 27.6%, but of course, these figures are always in evolution. This is for record cells tested in the lab, whereas modules in the field usually achieve a conversion efficiency of about 23–24%, a couple points lower. So our main goal is to go as high as possible in this value and also as fast as possible. So the main idea is to change or at least tweak the cell design in order to obtain higher efficiency. The first approach is the bifacial photovoltaic cell. In general, in conventional, also called the monofacial system, we have a backsheet made by plastic or in general polymers that shield the cell from environmental agents, but also block light incoming from the ground through its reflection. One other added benefit of the backsheet behind the module is to reflect eventual light that coming from the front of the module is able to escape to go through the whole module itself, through all its layers. So it also acts as a source of internal reflection. However, another approach would be that of removing this backsheet and replacing it with just another layer of glass behind the module in order to allow reflected light from the ground to reach the solar cell and be absorbed for energy harvesting. This technology is quite recent. It has shown up in the market in the last decade, but due to its simplicity but significant advantages, it has gaining an expanding market share, as we can see, and is expected to overcome half of the module installation in the next years. Sorry. Okay. So during my PhD activity, we have conducted a study in the field, and it was a comparison between a bifacial module and a monofacial module of the same technology, 3 cells in series for each module. Of course, these were bifacial cells, bifacial silicon heterojunction cells, whereas here we placed white cardboard in order to block the light reflected from the ground. And for these two systems, we measured the whole current voltage characteristics over a course of 3 days, simultaneously for both systems. The results of this study show that, of course, due to the additional light collected by the bifacial system, its current is higher, of about 1.5 amperes. That corresponds to a current production, current increase of 18% circa. We also measured the temperature of the modules, and we can see that there is a significant increase in module temperature for the bifacial cells of about 15 Celsius degrees. This is quite important because, first of all, it comes from the additional current that is collected by the system, because as we saw, the efficiency is not 100%. So, of course, some of this energy must be lost, and it is usually lost through heat. This causes the heating of the bifacial module. And in general, it can be shown that the increase in temperatures also corresponds to a slight decrease in the value of the band gap energy, and to a slight decrease in the open circuit voltage, which reflects also on the power production of the system. However, as we can see here, the additional current produced by the bifacial module is able to balance the open circuit voltage decrease from the higher temperature. And so if we calculate the energy yield over the day, we see that in the end, the benefits are stronger than the additional temperature of the bifacial system, and therefore we registered an energy yield increase of about 15%. If you look closely at the pictures, you will see that we have experimental data, but also a model that has been used to check the results of the experimental study. In particular, we used a MATLAB model of the system, which has previously been developed by the group of Dr. Lombardo. Let's have a look at this model. Here we see the inputs. Of course, we have some coordinates, spatial and temporal, of the system, the configuration of the system, but also the reflectivity of the ground, which will come in handy when calculating the reflected components. Of course, we have to calculate all these components: the direct sunlight, the diffuse sunlight, and, as I said, the reflected component from the ground. The first step is to calculate the position of the sun from the time and location of the system. In particular, we are interested in the zenith, azimuth angles that define the position of the sun, and the incident angle of direct light from the sun to the module. Then we employ some, let's say, well-established models in the literature, namely the Ashray models is a parametric model that through these three month-dependent parameters, and the A, B, and C, is able to determine the intensity of the beam component and of the diffuse component on a solar system, on a photovoltaic system. Here, just to guide you in reading this model, theta z is the zenith angle of the sun. However, we also have a tilted system, and in this case, beta is the tilt angle of the system, so the beam component has to be adjusted for the inclination of the system, and the diffuse component is adjusted by a factor that corresponds to the area of the spherical fraction from theta 0 degree to beta degree. This comes from the assumption that the diffuse light is diffused isotropically over all the 2 pi solid angle of the sky, and this is an assumption introduced by Liu and Jordan in the model named after them. So these quantities are the irradiance values of these components, but we also wanted to take into account the spectral distribution of solar light. In order to do so, we calculate the air mass value, which is the ratio between the height of Earth's atmosphere, about 10 kilometers, while at the numerator we have the length of the layer of air traversed by solar light, which of course depends on the time of the day, and namely on the zenith angle. So given this air mass value, we consider the standard solar spectra corresponding to air mass value of 0, which is essentially the extraterrestrial solar spectrum, and 1.5, which is a standard commonly employed in studies of this kind. And for a general value of air mass, we applied a linear interpolation between these two spectra in order to have a solar spectrum at any value of air mass, which means at any time of the day, at any position of the sun. And here we have this is a spectral distribution of solar light. Of course, we have also the constraint that the integral of this spectra must be equal to the beam component and to the diffuse component. In that way, we have a direct spectrum and a diffuse spectrum also of solar light. The most interesting part of this model is the calculation of the reflected light coming from the ground. To do so, we divide a certain user-defined surface into finite elements, and we calculate what is called the horizontal irradiance on each element, which is the sum of again, the beam and diffuse components, but on a flat surface rather than on the surface of the module, which is tilted by a certain angle. We assume that each ground element reflects a certain fraction of the incident horizontal irradiance isotropically, and we also took into account the spectral reflectivity of the material. In that case, in the case of the field study, it was common asphalt, which is more or less linearly increasing from ultraviolet to infrared wavelengths, with a peak of about 40% in the infrared range. So this reflected light is diffused isotropically in all the direction. But then we have to calculate the fraction of solid angle under which the ground elements, which is our reflected energy source, sees the cell in a module or a module in a string. And to do so, we employed this theorem by Louis Liais, which basically relates the amplitude of these angles in green to the solid angle of the tetahedron, which is obtained by the diagonal from one angle to the other of the module. So we basically have two half modules, and we are able to determine the solid angles for each, and then the sum gives us the whole solid angle, and therefore this is a factor that is applied to the spectrum of reflected light. We also need some electrical parameters of the system, namely the external quantum efficiency, which is the ratio of collected carriers over incident optical photons. We also need the dark saturation current, which is the expression of the strength of the recombination processes. And here we see how it all comes together in order to determine the short circuit current of the system. We have a contribution from the front of the module and a contribution from the back of the module. Here we see the external quantum efficiency of the front of the cell, and this is put in relation with the beam component, the diffuse component on the front of the module, and the reflected component coming from those ground elements that are, let's say, in front of the module, which means to the south of the module. We also have the contribution from the back of the module. We have a slightly different external quantum efficiency curve, which is usually lower than the one in the front due to the different contact grid, which shadows a little more the active area of the back of the cell. So this is a bit lower. Then we have the diffuse component that is impinging on the back of the module. That is the remaining part of the hemisphere. So from theta equal b degree to pi, basically. And then we have the reflected component from all those ground elements that are behind the module. That means towards the north of the module. So it is all integrated over the wavelength from 300 nanometers to 1100 nanometers. And all these are physical constants in order to obtain a quantity that is basically amperes. We also need to estimate the temperature of the model, and this is done again with a model that has been defined more or less in the 70s by Ross, which comes from a measurement of ambient temperature and makes use of a standard parameters, the nominal operating cell temperature, which is the temperature measured in a set of standardized environmental conditions. So here we have the sum of all the irradiance incident on the module, and this is the reason why, as we said before, bifacial modules tend to have a higher temperature, because we have all these additional components that are blocked by the backsheet in a monofacial system. Once we have all these components, we can obtain the complete current voltage characteristics of the system, and from these we are able to determine the efficiency, the generated power, the short circuit current, and the open circuit voltage. So this is the model that we employed. We also ran some other simulation in other studies in order to obtain some more insight on bifacial systems. Here we see a simulation where the same module has been simulated with different tilt angles ranging from 0 to 90 degrees over a whole year of simulation. And as we can see, the energy yield day by day depends, of course, on the tilt on the system. And we can see that the highest total energy yield over the whole year is obtained from tilt angles ranging from 30 to 50 degrees, because we can see that we have an energy production that is more or less high or significant over the course of the year. Whereas if we consider the most extreme cases, such as a flat horizontal module, we would see a higher production in summer, but also lower production in winter. Another study that we carried out was on eventual perimeter effects that may have an impact on the production in larger systems. In this case, we had a system made up by 6 modules in a 2-row by 3-column arrangement, which is usually called the landscape arrangement. And here we see the current produced by the back of the module against the width of the simulation area that we are considering on the east-west direction. And we have plotted this value for each module in the string. What is to be noted here is that there is a difference between modules, not only between the northern and southern row, but also between the module closer, let's say, to the sun. This simulation is carried out at 10 a.m., so the sun is slightly to the east of the system. And so the module 1, which is to the east, has a higher current than the corresponding module that would be module 3, that is to the west. This is, of course, because of the shadow cast by the module on the ground elements. Shadowed ground elements, of course, will not contribute to the reflected components of irradiance. This is quite of interest because when you have a string of modules, these are usually connected in series, and therefore the overall current of the system is constrained to the lowest of its contribution. That means that in this case, the overall back photocurrent of the system will be limited to these values, and this is all energy that is basically lost. Lastly, we have a study focused on the shadow that is cast by the module, and here we see some notable days of the year in spring and autumn, in summer and in winter. Here we have the fraction of shadowed area, and as we can see, we have low values in spring, in summer, but very high values in winter. This means that, as it is easy to imagine, in winter we have longer shadows. And while the result may not be surprising, this will come in effect when thinking or studying agrivoltaic systems. These are a new type of photovoltaic plant where the module itself are installed on basically on crop producing fields. So this has been shown to provide improvements in the crop production, because module basically shield the plants from direct sunlight, prevent, let's say, heating of the plants. So we have an increase in crop production. But of course, especially for seasonal crops, one must pay close attention to where the shadow of the module ends up. So we ran this simulation with the idea of providing some insights on how the shadow is cast by the module. Okay, so this concludes the first part of the presentation on bifacial photovoltaic systems. So let us cast aside the concept of bifacial cells aside for a moment, and let us focus on multi-junction photovoltaics. So in general, when a photon of high enough energy, higher than the band gap of the semiconductor is absorbed, of course, the excited carrier will end up, let's say, in an upper state of the conduction band. So as it moves towards the metal contacts of the system, all these excess energy will be lost through thermalization, that is, through interaction with the phonons of the semiconductor lattice. So if we consider the totality of the solar spectrum, we'll have a portion that has photons below the band gaps that are, of course, not absorbed by the system. But then if we consider the overall energy produced by the system, we'll see that these thermalization losses amount to a significant amount, even in the range where the photon is suitable for carrier production. So the idea is to, let's say, combine different semiconductors of decreasing band gap from the top in order to, let's say, match the band gap energy of the semiconductor with the corresponding portion of the solar spectrum, and reduce thermalization losses, as each photon, depending on its energy, is absorbed by a semiconductor with a close band gap energy value. So when designing these systems, on one hand, we have, let's say, the optical coupling of the semiconductor. That is a suitable choice of band gap energy in order to split solar light efficiently. But then we also have the electrical coupling of these junctions. And this can be mainly done in two ways, in series or in parallel. But this choice has a tremendous impact on the characteristics of the system. Here I report an example where we have, let's say, two solar cells, 1 and 2, which have different short circuit currents, but also different open circuit voltages. If I were to couple these two in series, we'd have a sum of the voltage output of the system, but as we said before, the current of the system will be limited by the lowest of the two contributions. So this means that in order to maximize the energy gain from a multi-junction system in series, you'd have you will need the same short circuit current from all its component junctions. On the contrary, if I connected the two cells in parallel, we have the sum of the currents, but the voltage will be closer to the lowest of the two. So again, in order to maximize the performance increase from this coupling, you need similar open circuit voltage values from the system. And we will see the impact of this choice in a bit. Before that, I want to show you the case study that I performed during my PhD activity. In this case, we had a two-junction system, and the goal of the study was to optimize power conversion efficiency, starting from a bottom silicon module, where the thickness of these layers are, let's say, common values employed in the industry and are therefore fixed. Whereas for the top module, we considered a different semiconductor, so different band gap energy, and the goal of the study was to optimize the thicknesses of all these layers in the top module. So in each layer, this is a Monte Carlo simulation, and in each layer, a photon can either be absorbed, if it is an absorbing medium, and or reflected or transmitted at the interface between each layer. A complex part it's basically the interface between the interlayer separating the two modules and the surface of the silicon module, because silicon modules in the manufacturing process are usually etched by chemical etching in order to reveal the 1-1-1 planes, obtaining this pyramidal texturing of the surface, which provides light trapping, increasing the photons that are absorbed in the system and decreasing the fraction of photons that is reflected by the surface. So while in general the simulation can be simplified basically with a 2D model where the interfaces are flat, a 3D simulation is needed when the simulated photon approaches this textured surface. In particular, we need the starting position and direction of the photon, and we calculate the intersection with the silicon pyramids, as well as with these boundaries which are employed to implement periodic boundary condition in order to simulate an infinite, in principle, surface of the silicon cell. That is, if the photon were to hit the boundary on one side, it would come out, let's say, from the other side, and that corresponds to simulate the adjacent pyramid in the surface. So once all the interactions with these surfaces are calculated, of course, the closest will be the real one, and the following steps will be based on what happens at this interface. So the simulation runs by 1000 photons per wavelength in this range. And as I said before, in absorbing medium, we have an absorption probability basically given by the remaining part of Lambert-Beard transmission law. And at the interface, we calculate the reflection and transmission coefficient through Fresnel equations. And then by generating a random number, we'll decide what happens to the photon and update its velocity vector accordingly to Snell law. Of course, we will need a transmitted vector and a reflected vector. The photon is simulated until it is either reflected away from the very first layer of the system, or is transmitted all the way through the last layer of the system, or absorbed by some of the layers in between. The simulation output is this type of plot where we can see the fraction of absorbed photon per wavelength. I report two, let's say, examples, just to show that once the wavelength approaches the bandgap, the corresponding bandgap energy value, the absorbance of the top semiconductor sharply decreases, and we have the beginning of the contribution from the bottom silicon module. As I said, we run this simulation for different configuration of the thicknesses in the top layer, and I report here the results. So the bottom module is made up by 72 cells in series, which is the standard commonly employed by modules installed in the field. And for the top module, we consider two cases. The Shockley-Kaiser ideal condition, where we have no contribution from non-radiative generation processes, and also, let's say, the state-of-the-art cells that we have at the moment. In order to do so, we considered the record efficiencies that are published in the literature, and we determine the ratio between the top efficiency that we have at the moment over the ideal efficiency that would be achieved in the Shockley-Kaiser condition. And this gives us a multiplicative factor for the voltage output of the cell. Of course, since the system is connected in parallel and we need to match the voltage of the two modules, we have a different number of cells in the two cases. Here we see the resulting efficiencies, and compared to the 29.4 limit of the single junction silicon photovoltaics, we see that higher values can be achieved by combining two different junctions in parallel. In this case, the highest values are achieved from a perovskite semiconductor of about 1.8 electron volt bandgap, and CGS, which stand for copper gallium selenide semiconductor of bandgap value between 1.8 and 1.7 electron volts. Okay. Now, for the final part of the presentation, we will combine the two approaches, the bifacial one and the multi-junction one, because in general, the bottom cell can, of course, make use of the light filtered by the top, but also from eventual reflected light coming from the ground. Of course, it is not possible for the top cell. So we realized a prototype, and in this case, we combined two gallium arsenide cells, each with an open circuit voltage of about 1 volt and an efficiency of 20%, and a custom-made bifacial silicon mini module. Here we cut these samples from a single silicon heterojunction cells and connected these three in series by soldering the contacts. So each cell has an open circuit voltage of about 1.7 volt. And so the combined open circuit voltage of this system is about 2 volts, whereas the combined open circuit voltage of the two gallium arsenide cells is of about 2 volts too. The efficiency of these cells is about 18%, starting from a cell of about 20%. This is because, of course, a mechanical cut procedure is likely to induce extended defects in the resulting samples. So we prepared the different mini modules and chose the best for the overall system. And these two components are again connected in parallel. Now, since these are already complete systems, it is not possible to, let's say, deposit one on top of the other. So the system is mechanically separated, and the optical coupling is achieved by installing two dichroic mirrors at an angle of about 45 degrees. So the idea is that these dichroic mirrors will reflect visible light to the gallium arsenide cells and transmit infrared light to the bifacial silicon cells. These cells will also receive all the reflected light coming from the ground. We characterized each component, and here we see the external quantum efficiency of the silicon heterojunction cells, which spans all the way from 300 nanometers to 1100 nanometers. We also see the quantum efficiency of the gallium arsenide cells, which sharply decreases at about 870 nanometers, which corresponds to the band gap energy of the semiconductor, which is of about 1.4 electron volt. We characterized the dichroic mirrors, so we measured their transmission and reflection, and we see a Catton wavelength that is of about 805 nanometers. So it wasn't possible to purchase components with the exact same characteristic wavelength as the wavelength of the gallium arsenide quantum efficiency. We are still sufficiently close to these values in order to achieve a good optical coupling of the system. Okay, here we see a picture of the complete bifacial multi-junction system. We can more or less identify the bifacial cells here on the bottom. These are the cases of the gallium arsenide cells, which are here. And here we have the two dichroic mirrors, and again, at an angle of 45 degrees. The system, because of the presence of these mirrors, will only, let's say, work appropriately with the direct component of the light. And for this reason, it was installed on a biaxial solar tracker in order to have incident solar light at the desired angle throughout the course of the day. Moreover, we also collected the direct solar spectrum through the use of an optic fiber connected to a monochromator with a solar cell at the end in order to register the current production at each wavelength, which corresponds, of course, to the impinging irradiance. Here we see the results of this study. We start from the open circuit value because this tells us if the coupling is optimal also from the electrical point of view. And as we can see, this value is quite constant, varying of about only 100 millivolts throughout the course of the day. We also collected some IV characteristics while covering the back of the silicon module in order to simulate a monofacial equivalent system. And we can see that there is a slight voltage increase in the bifacial configuration. We also measured the short circuit current, or rather we calculated it from the IV characteristic. And we can see a 20 milliamps current increase in the bifacial configuration. Of course, here the current trend is more pronounced with a variation of about 80 milliamps because this is dependent on the impinging irradiance on the system. Lastly, we have the efficiency, which has surpassed 25% with a 17% increase from the monofacial to the bifacial configuration. So these are the, let's say, electrical results. and let's have a look at the optical characterization of solar light. Here we see a portion of the spectra that we collected during the day, and we can see that the contribution of visible light decreases as we approach the afternoon. And at the end of the day, we have a significant contribution coming from infrared wavelengths. This is well expressed by the central spectrum value, which is basically the weighted average of the spectrum wavelengths. And we can see that this is relatively constant above 700 nanometers for most of the day, but then increases quite rapidly at about 800 nanometers in the afternoon. These spectra have been used to recalculate the short circuit currents of each components of the system, and we saw good accordance between the simulated values and the overall experimental currents registered from the system. This is quite important because if we look at the ratio between the calculated short circuit currents, we see a trend that is similar to the one of the central spectrum value, that is a constant value during the day and a sharp increase in the afternoon. This, of course, comes from the fact that each component is suited to a different portion of the solar spectrum. So when we have a higher contribution of infrared wavelength, the current contribution coming from the bifacial silicon cell will increase. What is the, let's say, main consequence of this fact? It is that if I were to connect these two components in series, I could, let's say, tweak the thickness of each component as I did in the previous study in order to, let's say, configure the system for this current ratio, which means bringing this value closer to 1. But then I would lose the electrical series coupling in the afternoon as the solar spectrum shows this redshift. Whereas we saw that in the end, the parallel coupling through the voltage match is much more stable. And that is because the open circuit voltage of a solar cell depends logarithmically on the inciding irradiance, whereas the current depends linearly. So when we connect the system in series, we have to take into account the stronger variations over the day of the contributions, whereas a system connected in parallel experiences very little variation in the output, in the voltage output of each contribution, and therefore it is much more stable. With this, I end my presentation, and as we take a last look at the references I employed during this presentation, I would like to thank you again, my supervisors, Professor Reitano and Dr. Lombardo, all the members of the commissions that are here today, Professor Lamia for all its support during this last month of the PhD, and of course all my colleagues at CNR and all of you for being here today. These are the last references that I employed, and I thank you all for your attention, and I'm open to questions if we have enough time.